Hello students, in previous lecture you have learned about the electronic configuration of transition elements. All of you know the transition elements are present in 4 transition series: 3D series, 4D series, 5D series, 6D series, isn't it? Then we will discuss detailed about the properties, electronic configuration, physical properties and chemical properties and periodic trends about the 3D transition series element. All of you studied about the electronic configuration of 3D transition series in detail. Then today we are going to study about the oxidation state of 3D transition series element. All of you know the elements in 3D transition series, that is scandium having atomic number 21, titanium 22, vanadium 23, chromium 24, manganese 25, iron 26, cobalt 27, nickel 28, copper 29 and zinc 30. Then oxidation state of scandium, titanium, vanadium, chromium, manganese, Fe, cobalt, nickel, copper and zinc. This 3D transition series depends upon the loss of electron from 4s orbital and loss of electron from 3D orbitals. If the atoms of the element loses electrons from 4s, if it loses one electron from 4s, then it forms m+1 oxidation state. If it loses 2 electrons from 4s orbital, then it shows m2+ oxidation state. And if the electrons from 4s and 3d, then it shows m3+, m4+, m5+, up to the m7+, m8+ oxidation state by those elements. Then see here, 3D series transition element shows common oxidation state, that is +2. All from scandium to zinc, they all shows +2 oxidation state. And all of you know the transition element shows variable oxidation state. When they shows m2+ oxidation state, that type of oxidation state, then atoms of those elements loses 2 electrons from 4s and it shows +2 common oxidation state. And if it loses 1 electron from 4s, then it shows m+1 oxidation state. But there is a common oxidation state of these series element is +2. Therefore, electrons from 4s, 2 electrons from 4s, it loses and shows +2 oxidation state. When it loses electrons from 3d, then it shows m3+, m4+, m5+, m+6 and m+7, as well as it shows m+8 oxidation state. Osmium, which is present in 4D transition series, it shows maximum oxidation state, that is +8 oxidation state. Similarly, we have to learn about the oxidation state, variable oxidation state of 3D transition element. Scandium shows +2 oxidation state and +3 oxidation state. Titanium shows +2, +3 and +4 oxidation state. Vanadium shows +2, +3, +4, +5 oxidation state. Chromium shows +3, +2, +3, +4, +5 and +6 oxidation state. And manganese shows +2, +3, +4, +5, +6 and +7 oxidation state, as it possesses 5 unpaired electrons in 3D orbital and 2 electrons in 4s orbital. if it loses all 2 electrons from 4s and 5 electrons from 3d, then it shows maximum oxidation state. Maximum oxidation state is shown by manganese in this series. Similarly, in 4d series, osmium shows maximum oxidation state, that is +8 oxidation state. From Fe to zinc, maximum oxidation state decreases. That means Fe shows highest oxidation state, that is +6. That means it shows +2, +3, +4, +5 and +6 oxidation state. Similarly, cobalt shows +2, +3, +4, +5 oxidation state. Nickel shows +2, +3 and +4 oxidation state. And copper shows +2, +3 oxidation state, and zinc shows only +2 oxidation state. Copper and chromium, it also shows +1 oxidation state, because in observed electronic configuration, chromium and copper possesses 1 electron in 4s. When they loses 1 electron from 4s, then they show +1 oxidation state. That is by chromium and copper, they shows +1 and +1 oxidation state. That is about the oxidation state of 3D transition series elements. Then see here, if scandium, when it does not lose its electron, then it is in atomic form. When it loses 1 or 2 or more electrons from 4s and 3d, then it shows M2 plus, M3 plus and M5 plus, M7 plus oxidation state. See here, scandium in electronic configuration of scandium, valence electronic configuration of scandium is 4s2, 3d1. Titanium electronic configuration is 4s2, 3d2. Vanadium electronic configuration is 4s2, 3d2. Valence electronic configuration for chromium, that is 4s2, 3d, vanadium it shows 3d3 electrons, and chromium shows possesses 3d4 electrons. Manganese possesses 4s2 and 3d5 electrons. In iron, 4s2 and 3d6. Cobalt electronic configuration, that is 4s2, 3d7. Nickel electronic configuration is 3d8, 4s2. Copper electronic configuration is 4s2 and 3d9. And for zinc, it is 4s2 and 3d10. But all of you know the anomalous electronic configuration of chromium, that chromium, observed electronic configuration of chromium is 4s1 and 3d5. It is because of when one electron from 4s enters into 3d orbital, then it becomes half-filled atomic orbital, which becomes more stable. Therefore, chromium shows the observed electronic configuration, that is 4s1 and 3d5. Similarly, copper, it shows observed electronic configuration, that is 4s1 and 3d10. Here also one electron jumps to the 3d orbital, and 3d orbital becomes completely filled and copper becomes more stable. Then when electrons from 4s, 2 electrons from 4s loosened by scandium, atom of scandium, then it forms the scandium 2 plus oxidation state, or it forms the ion, scandium 2 plus ion which having electronic configuration that is 3d1 and 4s0. Similarly, titanium when loses 2 electrons from 4s, then electronic configuration for titanium 2 plus ion that is 4s0 and 3d2. Similarly, we can write the electronic configuration for all those elements in M2 plus oxidation state. For vanadium, it is 4s0, 3d3 in plus 2 oxidation state. For chromium, it is 4s0, 3d4. Here 1 electron from 4s and 1 electron from 3d loosened by the chromium. Then it shows chromium 2 plus ion. Manganese having electronic configuration 4s0, 3d5 in M2 plus oxidation state. Iron 4s0, 3d6 of Fe2 plus oxidation state. Cobalt 2 plus oxidation state, it shows electronic configuration 4s0 and 3d7. For nickel, it is 4s0, 3d8. For copper, it is 4s0 and 3d9. For zinc, 4s0, 3d10. For Zn 2 plus ion. Similarly, we can write the electronic configuration of these elements in M3 plus oxidation state. We can write the electronic configuration for this plus 3 oxidation state. For scandium, it is 4s0 and 3d0 in plus 3 oxidation state. That means scandium 3 plus shows electronic configuration 4s0 and 3d0. See here, 4s orbital is empty, vacant, and 3d orbital is also empty or vacant. Therefore, scandium 3 plus is most stable ion, or plus 3 oxidation state is most stable oxidation state for scandium, because the orbital, vacant orbital of atom, they possesses more stability. Similarly, we can write the electronic configuration for titanium in plus 3 oxidation state. You have to complete the electronic configuration for those elements in plus 3 oxidation state. It is for your homework. Now we are discussing about the physical properties of transition elements. All of you know the transition elements are metal and they are colored metals, and they shows the characteristics, properties of metal. All of you know the general properties of metal, that is metals are generally having luster. Similarly, the transition elements, those have also luster because of its 3d orbital. 3d orbital of first transition element is successively filled. Few 3d orbital that is they are vacant and incompletely filled, therefore they shows luster. Then second one, they are hard. Metals are generally hard, but except zinc, cadmium and Hg. All of you know Hg, that is in liquid state at room temperature. Zinc, cadmium, those are soft, but except those elements, other elements are hard. Then they have metallic structure. They have metallic structure. All of you studied the lattice structure of the elements. Lattice structure of the elements, which those transition elements shows metallic structure, except zinc, cadmium, Hg and manganese, because they have completely filled 3d orbital or half filled 3d orbital. Manganese has half filled 3d orbital, and zinc, cadmium and Hg has completely filled n-1d orbital. Therefore, they does not shows the metallic structure. Then all of you know the common properties of metal. That is, metals are ductile. Similarly, those elements are also ductile and malleable. These transition elements are good conductor of electricity and heat. They having high density as well as they have high melting point and boiling point. High melting point and boiling point. These are the physical properties, that is of the transition elements. Now we will discussing on trends in atomic properties of first transition series elements. All of you know the trends in atomic properties are atomic radii, ionic radii, ionization enthalpy, magnetic properties, electronegativity, electropositivity, oxidation state and valency, etc. Today we are going to study about the atomic radii, ionic radii, ionization enthalpy, about the first transition elements. First of all, see the atomic radii and ionic radii of first transition elements. All of you know the atomic radii means it is a distance between nucleus and valence electron, that is outermost electron of an atom of an element, is called as atomic radius. Then atomic radius is measured in picometer, that is pm, nanometer, nm, or it is measured in angstrom. Then atomic trend in atomic radii in first transition series element, that is from scandium to zinc. That means in first transition series element from scandium to zinc, atomic radii, it is gradually decreases from scandium to zinc. See here, atomic radii of scandium is 164 pm. For vanadium it is 135 pm. For iron it is 126 pm. For cobalt it is 125 pm. And for zinc it is 137 pm. See here, atomic radii from scandium to nickel, it is decreases, and it is sudden increase in the atomic radii of zinc. There is some variation. It is because of zinc possesses 3d 10 electrons, that is completely filled 3d orbital. See here, atomic radii from scandium to nickel, it gradually decreases, and beyond the nickel, copper and zinc, atomic radii increases slightly. It is because of their completely filled 3d orbital. Then similarly, ionic radii, it is also decreases from scandium to up to the nickel, that is gradually it is decreases. That means atomic radii in first transition series element as well as second, third and fourth transition series element, it decreases from left to right, and there is some variation. It is due to the few concept which is beyond that syllabus. Why atomic radius of these element decreases gradually? Because all of you know the nuclear effective nuclear charge from left to right, that is scandium to nickel, it increases by 1 unit. It is because of 3d orbital is successively filled up, progressively filled up. One extra electron added in 3d orbital from scandium to zinc. Therefore, effective nuclear charge increases from left to right. As effective nuclear charge increases, then pull of valence electron towards nucleus. Therefore, atomic radius or ionic radius decreases. And there is one more reason, that is all of you know 3d orbitals of those elements are successively or progressively filled up, and this shows variable oxidation state. The d orbital is less penetrating and more diffused. Therefore, this shows the less or low screening effect, and therefore nuclear effective nuclear charge increases from left to right in these transition series. Therefore, atomic size or ionic size gradually decreases from left to right in those series. Ionic radii, that is this periodic trend is explained on the basis of two different concepts, that is ionic radii of elements, ionic radii of elements of same oxidation state, and second one concept, that is ionic radii of same element, ionic radii of same element in different oxidation state, See here, ionic radii of elements of same oxidation state, that means chromium 2 plus having ionic radii, that is 82 pm, and copper 2 plus it having ionic radii, that is 72 pm. See here, the elements with same oxidation state, that is 2 plus oxidation state, chromium is left to the copper and having ionic radii 82 pm, and copper 2 plus, this ion has ionic radii, that is 72 pm. That means it is decreases from left to right because of effective nuclear charge increases from left to right. Therefore, ionic radii also decreases from left to right. One more concept, that is ionic radii of same element in different oxidation state. The same element which having M2 plus, M3 plus, M4 plus, M5 plus, and so on oxidation state, and ionic radii for the same element having +2 oxidation state, +3 oxidation state, +4 +5 oxidation state. Ionic radii for those also decreases from lower oxidation state to higher oxidation state. It is also because of effective nuclear charge increases as the oxidation state increases. Higher the oxidation state, effective nuclear charge increases. Therefore, ionic radii decreases from lower oxidation state ion to higher oxidation state ion.